Director of the NSF Scholarships for Science, Technology, Engineering, and Math. He's been on the Oxy faculty since 1994, serving as a department chair twice, and he became full professor in 2014. He actually began his career at Oxy as a minority postdoctoral scholar in residence. Ron holds math degrees, both PhD, master's, and bachelor's from Rensselaer Polytechnic Institute. His research interests include mathematical modeling, applied math, numerical analysis, math education, data science, and the scholarship of teaching and learning. He's published peer-reviewed articles in journals such as Data, Notices of the AMS, and Numerical Methods for Partial Differential Equations. He's a passionate advocate for broadening the participation of underrepresented individuals in mathematics and STEM, and we're so happy that he can join us and give our inaugural talk. So Ron, the floor is yours.
Thank you, Anthony, and I'm really happy to be here. So the title of my talk is Different Differences, and it's set into 3 different parts. I'll be talking about different differences in the context of mathematics. That's the mathematics research that I do, where I talk about difference equations and different kinds of difference equations that are used to solve get very good approximations of differential equations. I'll spend about 15 to 20 minutes on that section. And that mathematics is intended to be accessible by anyone who has taken calculus. Then I'll move on to talking about different differences and how they intersect with me, my different identities. And I'll give a sort of brief overview, or I guess a longer overview of my career trajectory than Anthony just talked about. And then I want to end the last 5 minutes or so talking about different differences in the mathematics community and how different people are allowed to or do participate in the mathematics community due to these standard differences and non-standard differences that we all have. And I'll make some, I'll provide some data and make some suggestions for how things can be different. Okay. So we're going to begin with a short primer on approximating derivatives. So you may remember from Calculus 1 that if you want to find the derivative f prime of x of a given function f of x, there are multiple formulas we can use. We often call them difference quotients. The first is the forward difference quotient. That means you try to approximate the derivative by evaluating a function a little bit ahead, f of x forward, f of x plus h, subtract the where you want to know the derivative, f of x, and then divide by the difference. So it's the forward difference, it's the sort of standard one that people recall, hopefully. And then there's a backward difference, which is very similar, except h is sort of changed to negative h. And there's also a center difference formula. There's many other difference formulas as well, but these are the standard difference formulas. What we're going to be looking at is changing from a continuous function f of x and approximating it by a discrete, a set of discrete values u sub k. So we're going to take a function that's defined on an interval from a to b, split it up into n pieces. This is often called partitioning. And what we're going to want to do is we assume that the function is continuous and multiply differentiable everywhere. And at some point, x sub k will have a value f of x sub k, and we'll call that u sub k. And we'll do that for all the k's from 0 to n. So when we do that, there are discrete analogs of the difference quotients that we use for the f of x function. And we can write them in terms of the u sub k points. So just like there was a forward difference quotient, there's a discrete forward difference. Instead of f of x plus h minus f of x over h, you have u sub k plus 1 minus u sub k over h, so neighboring points. And then in addition to a discrete forward difference, oops, I forgot to start my clock. There is a discrete backward difference, and there is a discrete center difference. And what we're going to do is these are all standard finite difference formulas. We're going to try to use these approximations to approximate derivatives in differential equations in order to produce difference equations. Differential equation sounds like a fancy term, but it really is just an equation that has a derivative in it. Here's an example. which I like to call the calculus student's favorite example, in that one of the cool things about differential equations is that the solution you're looking for is a function. In sort of algebraic equations, you're usually looking for a value which makes your equation an identity. In a differential equation, you're looking for a function, an unknown function. I like to call this function pat. And what you're told is that we don't know much about pat, but we do know that the derivative of pat is equal to pat. In other words, dy dx equals y. So there's some mystery function pat. So when I take the derivative, I get pat back. Also, when it becomes an initial value problem, we know one thing about pat. We know if pat inputs 0, it outputs 1. And it's pretty clear then that pat has been revealed, and it's the exponential function e to the x. And so oftentimes in applied mathematics, when we're looking at numerical methods, we apply them to easy problems or problems that we know the solution to, because what we're going to do is, it's a very general technique. If you have a problem that's too hard for you to solve, we say, I don't want to solve that problem. I want to solve an approximate version of that problem. I'll use my numerical techniques on the approximate problem, and then I'll slowly make my approximate version of the problem closer and closer to the problem I wanted to solve, hoping that the easier techniques I'm using to solve the approximate problem will produce approximations to the solution that get closer and closer and closer to the actual problem I want to solve. We're going to do a very similar process here in that instead of solving the differential equation, we're going to solve the difference equation. So we're going to approximate these derivatives, the dy dx, by the discrete forward difference, y sub k plus 1 minus y sub k over h. And here, instead of having to do integration or guessing that the mystery function whose derivative equals itself, we can just use algebra. So we're going to solve for y sub k, we can just do some math. I'm not going to be, I'll be showing these steps, but I'm not going to be walking through these steps. And so it turns out that the exact solution to the approximate version of the initial value problem is in blue here, and it's y sub k equals 1 plus h to the k. So y sub k is similar to the u sub k in the picture I showed before. It is discrete values that are known at particular k values for every value from 0 to n. And here's a graph of what that would look like if n was 10. So the red curve would be the exact solution. There's pat in all their glory. And compared to that is our approximate solution in blue, that's 1 plus h to the k. And as we can see, at x equals 0, y equals 1, they're right on top of each other, because we said pat had to output 1 when x was 0. And as you go away from that place, the two diverge. The blue circles are away from the red line. And we'd really like the blue circles to be right on top of the red line, or at least the difference to be small. And that gets us to a point of how do we measure what our error is? What a mistake we are making. Because remember, our algorithm is that we want to sort of make that difference as small as possible. But what we've done is we've approximated this continuous interval from 0 to 1 by 10 values, actually 11 values, from 0 to 0.1, et cetera. And so we're pretty sure that as n gets larger, the error should get better. And we'll see if that happens. But first, let's talk about what we mean by error. What we mean by error is we have the exact solution, pat, y of x equals e to the x, and we have a discrete approximation to that, y sub k equals 1 plus h to the k. We have to compare them at the grid values. So we say that the error is the difference between the exact solution evaluated at x sub k minus all of the y sub k's. And so therefore we'll have an expression that depends on k, and this will be that difference. Here's a graph of what that looks like. And as we expected, as the number of points increases, as your n goes from 10 to 20 to 40 to 100, in the limit as to infinity, the difference between the exact solution evaluated at discrete points and the discrete solution evaluated as an approximate version of the differential equation, they get closer and closer, and in the limit they go to 0. This is not surprising, this is not a hard problem, but it's useful to know that we can do standard finite differences and solve an initial value problem. But what I want to talk about Oh, right. So then I want to summarize what we've been doing. Really what you're thinking about is that we have an ODE, or differential equation, and a difference equation, or I call it an O delta E. And you can, each of those equations, you can solve exactly. In the case of the ODE, you get an exact function, which is in black, y of x. And in terms of the O delta E, you get a discrete expression, or discrete values, y is okay. Those were the blue circles. And when you approximate or evaluate the exact solution at the discrete points, you get y of x of k. And the whole, one of the key points, the key algorithm, the key sort of idea of numerical analysis of differential equations is to try to make that little green approximate as small as possible, to make the red y of x okay and the blue y is okay get closer and closer and closer. And the limit, they should be exactly on top of each other. So now we want to talk about different kinds of differences. We did that problem with standard finite differences. Professor Ronald E. Mickens of Clark Atlanta University is an African-American mathematical physicist who back in the 80s suggested, let's use some other non-standard forms of difference quotients. And he suggested that we introduce these functions phi sub 1 and phi sub 2. You might note that if phi sub 1 and phi sub 2 are both just h, that expression would just become the forward difference quotient. And so why this is useful is that it gives us lots of freedom to pick phi functions that may produce, may have better qualities of approximating the behavior of the derivatives in the differential equations that we're looking at. And there's a discrete version of Professor Mickens' non-standard difference schemes, which is down below. And there, the key idea is phi of h is what's known as a denominator function. And when you pick different kinds of denominator functions, that's how you get different kinds of non-standard differences. So these things are often known as NSFD schemes or non-standard finite differences, or I've been promoting the idea they should be called Mickens differences or Mickens discretizations. Yeah, and so here's some examples of the denominator function. H would be the standard one, or sine of h, e to the h minus 1. All these functions, what you notice about them is that in the limit as h goes to 0, they have to be 0, and they have to be what we call big O of h. If you were to approximate them, their first term needs to be h, because eventually they really need to look like, in the limit, as a regular difference quotient. You still have to end up with a derivative when you're done. So let's try to get a non-standard finite difference scheme and apply it to the problem to find pat as we did before. So we have dy dx equals y, y0 equals 1. Since we, and this is what one of the key ideas of non-standard finite difference schemes is, we know the solution of this problem involves an exponential. So why not pick a denominator function that has an exponential in it? If we pick phi of h equals e to the h minus 1, then instead of replacing dy dx by y sub k plus 1 minus y sub k over h, we'll replace it by y sub k plus 1 minus y sub k over e to the h minus 1. Then, as before, the cool thing about difference equations is that you can just, oftentimes you can just use algebra to solve the solution, to find the value, to find the functional representation of y sub k in terms of k. And so here we do some algebra. We get the value of y sub k. Again, I'm just zipping through the algebra. And here it turns out that the discrete version, the exact solution of the discrete version of the differential equation, in other words, the exact solution of the difference equation, is exactly y sub k equals e to the kh. And here, as I tell my students, your spidey sense should be tingling, or your mathematical intuition, because that should look very familiar. Because remember, before when we did a discrete version of pat, and it was in red, it was y sub k equals e to the kh. So yes, dear listener, we have found a discrete term that is exactly equal to the exact solution. In other words, if we look at the error done by this Mickens difference of this simple problem to find pat, it turns out that it's identically 0 everywhere. The two things are the same. And this is really the best of possible worlds for a numerical analyst. So we thought we were going to, we did solve an approximate version of the differential equation, but it turned out that our solution to this approximate version of the differential equation is exactly the exact solution. So we didn't have to worry about our having n go to infinity. For every value of n, we will be getting an exact solution. And this is very cool. When I discovered this, when I was back in graduate school, I didn't realize this could happen. I'd always thought that, you know, when you do numerical approximations, they're approximations, not that the approximation will be zero. I mean, will be exactly identical. And so is this a fluke? No. Mickens has published an amazing 300 papers and over 10 books in the last 30 years, not all on non-standard finite differences, probably the vast majority. He, as I said, he's a physicist, not a mathematician. But his work has been in nonlinear oscillations and applications of finite difference schemes to a dizzying array of problems that derive from describing real world phenomena. And in many, many, many cases, he has shown that you can produce exact finite difference schemes for these problems. And even when you can't, the fact that you have an exact finite difference scheme for a particular problem, if you are tweaking that problem to be something harder, it's likely that the finite difference scheme that you had for the slightly tweaked problem will do better than a standard finite difference scheme for the slightly tweaked problem. Okay, so I don't want to give you the impression that the only way to do non-standard finite differences is through denominator functions. There are actually, Professor Mickens has 4 rules of finding non-standard finite differences. And here's another one, which is the idea of using non-local discretizations. So here's another sort of toy problem. It's also an initial value problem. This time, instead of looking for Pat, we'll look for Chris. So Chris is an unknown function, big T, and all we know about the derivative of Chris this time is that it's negative lambda square root of T. And so this immediately raises some concerns that we're taking the square root of T. This is a real world phenomenon, so we want T to be real. So T is always gonna have to be positive. It's gonna be non-negative. And what you can see really is that if the derivative of T is always negative, then that means T is always decreasing. Hopefully remembering that from Calculus 1 as well. And so what this problem says, what phenomenon is being described here is that Chris starts off at some value, T sub 0, and then decreases. Eventually it's gonna hit zero. It's gonna hit 0. And then once it hits 0, it has to stay at 0. Because if Chris outputted a value less than 0, then this differential equation wouldn't make much sense. Again, I call this a toy problem because it's not hard. The solution's right there. It's a parabola. But it has interesting behaviors, right? We know that there's some magical T star value, the length by which, how long Chris takes to start wherever it is and hit 0. And then from then on, Chris is 0 going on. And so we want is a different scheme that not only gives us the behavior of Chris, but also provides that the approximate solution also has the behavior that the exact solution has. Here's what the graph of, here's a selfie of Chris. So it decreases and then hits 0. And here's a technique for finding Chris. So we know the exact solution of Chris is T of T equals a quarter to square root of T naught minus lambda T minus T naught squared. If we make these transformations, wherever we see a little t, we turn it into the red tk plus 1. Wherever we see a t sub 0, turns into a t sub k. Big T sub 0 turns into big T sub k. What's interesting here is that we're not using local discretizations. By local, I mean usually we're only interested in knowing things at T sub k, or in the previous version it was x sub k. By making these interesting transformations on the exact solution, we'll do some algebra, and we get this expression, T sub k plus 1 equals T sub k minus lambda h squared root of T plus lambda squared h squared over 4. Now we know this must be an exact finite difference scheme because basically we just discretized the exact solution. We discretized the functional version of Chris. But if you rearrange that equation, you'll see that if you look at equation 3 and equation 4 is what you would have gotten if you had just replaced derivative of t, the left-hand side of our toy problem, with the discrete forward difference. And if you had done a local discretization of the right-hand side. But the exact solution of this differential equation and the difference equation is if you have this purple term, lambda squared h to the fourth. And there's no way you would have thought, if just by looking at equation 4, like why would you think to put in this purple term? So what happens is that by using non-standard finite difference equations, again, we have another example of an exact finite difference scheme, but it shows that they're really, they're almost magical. They produce exact finite difference schemes, and they're very different. It's not just you're doing some kind of transformation or change of variables on regular difference equations. Non-standard finite difference equations are something else. Okay. Looks like I'm good on time. Oh, right, but I did start my clock a little late. So I was gonna skip this, but I think I'll just do it rather quickly. So my latest research is another method for working out non-standard finite difference schemes. Again, it involves this toy problem, and it thinks about looking at 1 and thinking about, there are many different ways of approximating 1. And if we think of 1 as a function over a function, then if we use, again, a non-local discretization, we can come up with a non-standard finite difference scheme that has properties that we want. Remember, we wanted Chris to always be above 0. We call that positivity preserving, or Mickens does, and we use that expression. And so we can come up with a non-standard finite difference scheme which has that property. What happens though is that, so this is a graph showing, right, here's Chris, the black line, the exact solution. Standard is the circles, and the two non-standard finite difference schemes are, the asterisk and the green diamond. You can see they're all really, really close. You can't really tell much from this view. So let's look at the error, right? The error is the difference between the exact solution and each of the discrete terms. Here, there's a different story. What happens is that, remember, the scale is very small here, relatively small. There's about 100 points. What we want the solution to be close at 2, right? Because 2 is where something happens, right? 2 is where where Chris hits 0 and then stays 0 forever. It turns out in this case, the standard differencing is doing the best. It's better than either the second NSFD scheme, which I just showed you, or the first. The first is actually giving a lot of error. And I wanted to include this to say, when you do non-standard finite difference schemes, they're not always better than the standard finite difference scheme. Oftentimes they are. There's many different reasons why you do non-standard finite difference schemes. Sometimes they give you more efficient computations. Sometimes they do give you an exact finite difference scheme, and sometimes they don't. You basically have to come up with the schemes using Professor Mickens' rules, and then do the numerical experiment and see what happens. I don't want to leave you with the impression that all I do with non-standard finite difference schemes is solve somewhat trivial problems. So here are some examples of some more interesting problems that I have solved in the past in my career. One of them is the planar Bratu problem. The Bratu problem is a long-standing numerical problem that people look at because it's a nonlinear eigenvalue problem, this lambda. It's very nonlinear because it's e to the u, that's the mystery function. And it has a bifurcation where for most values less than a specific value, a critical value of lambda, you get 2 branches of the solution. And at the critical value, you only get 1. And any value after the critical value, you get no solutions. And it's very hard for numerical solutions to resolve that behavior. And standard differences doesn't. And my work showed that you can come up with non-standard finite difference schemes that resolve the behavior of the solution of the planar Bratu problem much better than standard differencing. So when I did the planar Bratu problem, and then I looked at the cylindrical Bratu problem, which is called the Bratu-Gelfand problem, it has some more interesting features because it's in cylindrical coordinates, it has a bad singularity at r equals 0. Another problem I've looked at is a nonlinear diffusion problem, which comes from plasma physics. And this is a publication with Professor Mickens himself and an undergraduate student, actually. And this is where this toy problem came from, because the nonlinear diffusion has a square root term in it. And there's even more complicated version of this in plasma physics, where it's really, there's multiple fractional terms in the partial differential equation. And then way back when I was just a wee lad, my PhD work was in computational aerodynamics. And this is where I actually thought I had invented non-standard finite difference schemes. I switched from doing standard differencing to doing a sort of a funky difference is what I initially called it. And I thought, oh, no one else had done this before, because I had to resolve a particular nature of the numerical. This is trying to find the stream function phi, very, very, very close to r equals 0, and it's very, very, very non-singular. I changed up standard differencing, and it worked. There's no known exact solution to this problem, but it got better results than we'd expected. And I was I was sort of happy and sad to discover Professor Mickens had been there way before me, and he had many, 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 many different examples of doing something similar. And then I knew that the term was called non-standard finite difference schemes after that point. So that's the end of my first section of talking about mathematics. Now I'm going to talk about how different differences impacts my identity. And so I think of this in terms of also standard differences and non-standard differences. Standard differences, if you were to take a screenshot of this presentation, you'd probably be able to tell my race and gender. Those are sort of standard differences, those are visible differences. But you might not be able to tell my non-standard or invisible identity characteristics. What's my ethnicity? What's my sexual orientation? What's my gender identity? What's my immigration status? If you're curious, here they are. So I am a Black male, African-American. My ethnicity is, I'm Caribbean. I no longer have the accent, but yes, I was born a West Indian. I'm hella gay, is my sexual orientation. Gender identity is also male. I'm a naturalized US citizen. So again, these non-standard identity characteristics are something that you may not be able to tell just by looking or listening to someone. I'm not first generation because my dad has a PhD. And my class, I'm a college professor and dean at this point. So my class can't be considered, I just say I'm married, I have 2 incomes, no kids, and 1 fur baby. So I want to talk more about how my different differences, what I just went through, it has impacted or has not impacted my career trajectory by doing a sort of hopefully speedy run through my career trajectory. So as I said, I was born in Grenada, a little island in the West Indies. Before the age of 2, moved to the United States because my dad wanted to get his PhD. Then he moved us to Barbados, another island in the Caribbean. There I graduated from Combermere. Combermere School is older than the United States. It was founded in 1659. And there is another relatively famous alum from Combermere. Her name is Robin Fenty. You may know her better as Rihanna. So yes, Rihanna and I do have something in common. And so that's getting to the gay part again. In '86, I went to RPI. I co-founded something called Homo Radio at WRPI 91.5 FM when I was just entering graduate school. I also created the Queer Resources Directory in 1991 back then. This is before there was a World Wide Web. For you kids out there. I then graduated from RPI with my degree, 3 degrees in 8 years. In 1997, the QRD was a successful co-plaintiff in one of the first lawsuits against Congress's attempt to regulate free speech on the internet, called the Communications Decency Act. Because we were a repository, the QRD was a repository of basically all things queer on the internet, we would have, some of our material would have been affected by the Communications Decency Act, which was struck down 7-2 by the Supreme Court. After graduating from RPI, my first job was minority postdoctoral scholar in residence at Oxy. Then I became an assistant professor. Then I became an associate professor, tenured 8 years later. Then I became chair. While I was chair, I co-founded a Black LGBT advocacy organization in Los Angeles. In 2011, I was named an LGBT Educator of the Year by the National Organization of Gay, Lesbian Scientists and Technical Professionals. In 2011, I went to the National Science Foundation for 2 years. When I came back, I was promoted at Occidental College to full professor. And then I took a permanent position at NSF, but it only lasted 2 years because I was lured back to Occidental to become a dean, which is what I am now. And so this quick run through my career trajectory and sort of highlighting sort of the I would not call them unprofessional, but maybe non-professional things that I did during that time leads to this question: how was my career trajectory perturbed or affected by my identities or my standard differences and non-standard differences? I would say it's complicated. I do think that my sort of delays in making sort of professional advancement and getting tenure and getting promoted was sort of negatively impacted by various aspects of my identities. But I also think that getting the job in the first place and sort of going to NSF and because of my identities, being interested in doing different things, like leading to the creation of the Queer Resources Directory, being involved in a Supreme Court lawsuit, founding organizations, that took time away from other things, but as a whole, I think, I definitely think it was worth it, and I wouldn't really do much things differently. Now I want to talk briefly about the ways that differences affect the mathematics community as a whole. So I want to leave you with 4 specific ideas. The first is mathematics is a human endeavor. I am strongly skeptical of people say, oh, math is objective. It doesn't matter who does the math. Math is whatever you say, 2 + 2 = 4. And I would really question that. When you're saying someone writes 2 + 2 = 4 on the board, well, who's doing that writing? Who is that person? And who are the people in the room looking at that? Math is done by people, and it matters who those people are. The way Francis Su says this is mathematics is for human flourishing. In other words, mathematics has beauty, mathematics creates joy, mathematics should be used to enrich the lives of all the people who do it, who see it, who interact with it. I think of that in saying mathematics is for solving problems. I say that from the perspective of an applied mathematician that I am, but I think pure mathematicians also, when you're thinking about proofs, when you're analyzing abstract concepts, it's still solving problems, maybe problems that don't come from or inspired by or are trying to describe real world phenomena, but you still are solving problems. And overall, it really matters who does the math. And let me talk to you about who does the math. Here's some data from the Department of Education. And this is over the last 15 years. I want to make very clear, these are not percentages. These are nominal numbers. To me, this data is disturbing and embarrassing to the math community. So in 2006, there were 5 US-born Black female mathematicians who earned PhDs. I know 4 of those people personally. I mean, you can put names to faces to this data, and that is incredibly problematic, I think. And so this data is just, it's an indictment, I believe, of the mathematics community. So when you think about equity, diversity, and inclusion issues in the mathematics community, you're talking about these people, these numbers. Here's the numbers for Black men. Again, they're higher because there is a gender difference in math PhDs. But again, these are just US citizen representatives, US citizen recipients of PhDs. Now there's more males than females. And the total between the two is about 900 to 1,000, and there are about 1,200 to 1,500 PhDs given every year. So this data is horrible. We need to improve it. I'll show you some data of what's happening with bachelor's degrees in the US to show that where we're going, because presumably people who get bachelor's degrees will, some of them will eventually get PhDs. In 2018, we're approaching the, no longer will be a minority of people who are getting bachelor's degrees in mathematics will be white. The percentage of people getting bachelor's degrees who are Latinx or Latina is approaching 10%. It's increasing. The trends are in this direction, and the African American trend is not good. It's actually been, it's first of all, it's very small, 5%. In the United States, 13% of the population is about African American, and about 14 to 15% is Latino. And so these numbers, when we say underrepresentation in math, this is what we mean. And so what I would like to argue is that we really need more data about standard differences to be collected and distributed widely in the mathematics community, so people know this data. But also, it's not just this data that I showed, which is actually really hard to find. There is no source of data that would tell us what is the percentage of tenured faculty members in the top 100 universities that are female, or that are Latino, or that are Asian. That data source does not exist. And this is incredibly problematic if we're going to do effective EDI efforts in the math community. And why should we stop at standard differences? We should also have data on non-standard differences: sexual orientation, ethnicity, first generation status, and other identity characteristics should also be included by the math community. And I'm just about done. I want to thank Anthony Bonato for his leadership in organizing LGBTQ+ Math Day and for inviting me to participate. I would like to thank everyone at the Field Institute for everything you've done and continue to do to support the entire math community. It's well appreciated, and I hope other mathematical institutes take your lead and follow it. I want to thank the audience for your attendance and attention. That's all, folks.